Hola,
Hola, Karina. ¿Cómo
hola
estás?
profesor, ¿cómo? ¿Bien y usted?
Bien, bien.
Hola, hola.
¿Qué-
Hola.
Profe, tengo una duda con respecto a la tarea.
Cuéntame.
En el problema 1b pide calcular, dice, calculate the effective difference in optical dip. Eh, what do you mean?
Un momento. Um, 1P. Ok. ¿Cuál es la diferencia entre tau por sea level y 0.80?
Yeah, pero difference mean tau 1
Eh,
minus tau 2, tau 2.
sí. Ya, no entiendo. Y aparentemente el punto es para comparar. Y
Sí.
ya, no necesariamente tener una diferencia necesariamente, pero compararlo.
Ya, entonces puedo sacar, no sé, la división de los dos.
Sí.
Ya.
Sí. Ya, puedo aumentar una clarificación sobre esto. Bueno, ya, efectivamente puedes calcular un cambio entre tau, eso es la diferencia.
Ya.
Si hay, por ejemplo, hay un tau por sea level y hay
Ya.
un tau por cada 1 kilómetro
Ujú.
y tau va a reducir, ¿cierto? Y
Sí.
puedes medir la dirección.
Ya.
Okay, looks like we have everybody.
Hello.
Hello. Do you have any doubts, questions before we start? No. Sí. Yeah. Right, so we were talking about, well, basically we were deriving the Larmor formula, which was a very classical way of thinking about how a charge will generate radiation. So let me go back to that. Okay. Right, so we had just thought about having the situation where we move an electron, we give it an impulse, and then the field is propagating out, and that propagation of the electric field out and the incongruity of it at some point, right? There's going to be a signal that propagates out, which is a change in field. And that change in field will be different for someone who's here, an observer here versus an observer here. The field doesn't change in this direction, but it changes in this direction. Actually, technically that's not true. It gets a little bit stronger because the distance between us and this particle is different. But for here, you change sort of radially. And so one can kind of calculate this change. And so it looks something like that. And so we're talking about a change perpendicular to the direction of acceleration. And so if it's accelerating this direction, then we're talking about a change in this direction. So we can calculate that, and sort of plugging in some basic sort of equalities, we can end up getting a value for this electric field, which goes as 1 over r, as opposed to the radial field, which goes as 1 over r squared. And so if far away from your charge, all you really see is this one dominate over this. And so we could calculate what the flux was of this, and we ended up with something which looked like this. And so this is the amount of energy that is flowing out, and we can equate this with a photon. And this situation looks something like this. So we have a particle which is moving in this direction, and the fields are going to be strongest, the amplitude is strongest in the perpendicular direction, and the amplitude of this flux is lowest parallel. And so this sort of dipole looking thing is representing the amplitudes as a function of angle. Right? And at any given angle, so at a given angle of theta, you have some solid angle that's being projected out with this flux. Okay, so this sort of conveniently describes how a accelerated charge will radiate. But again, it's a very classical derivation. So I also showed you this, so in 3 dimensions, it looks something like a donut, right? And this is, again, just the amplitude. So we can calculate this power emitted, which is just summing over the solid angle, right? If we take the entire sphere or surface area with this flux, we end up getting the total power that's radiated. And so we can do this integral, plugging in this thing here, which is this Poynting flux as a function of angle. And we integrate over d theta and d phi, and we end up with an integral over sine cubed. And this integral reduces just to a value of 4/3 via a lookup table. And so magically you end up with the total power radiated is a function of the charge squared and the acceleration squared. So the faster it's accelerating, the more irradiation is generated. Right. And so this is the total power emitted. This is what's known as Larmor's equation. And so generally what it's telling you is that if you have a charged particle, if it's accelerated by any means, via electrical forces, magnetic forces, it's going to radiate. And that radiation is proportional to the square of the acceleration. And so the faster the acceleration, the higher the amount of radiation that's going to come out from this. And so when you have things that are relativistically accelerated, you can get very large amounts of energy coming out per second. So this is super important because it's a very generalized thing where you take a particle, you take a charged particle and you accelerate it, you'll generate radiation. This, in theory, should work both for electrons and for protons, right? However, because protons have a large mass compared to electrons, the amount of energy you need to dump in to change its momentum and accelerate it to the same acceleration as the electron is a lot, right? And this is because protons are something like 2,000 times more massive than electrons, and so typically you need energy, which is the square of that. And so if you have something that's in equilibrium, electrons and protons interacting with each other, typically what you'll end up having is that the proton will stay almost stationary. The electron will move very, very fast. And so in general, in something that's in equilibrium, the electrons will typically be radiating about 1 million times stronger than the protons. And so we can effectively just neglect protons. Right? If we have a plasma that initially was neutral and we ionized it, photoionized it, right? We have equal numbers of protons and electrons. The electrons are moving around very, very fast, and the protons we can essentially consider them stationary with respect to generating radiation. Okay, questions? This ends up being very, very fundamental, and we'll come back to it again and again. Okay, so those were the last 2 slides of the last lecture I didn't quite get to. And so here we are at the start of this lecture. And so, as I mentioned, this will be the basis for all of our derivations of free emission, which is electrostatic Coulomb interactions, and synchrotron radiation, which is magnetic field electron interactions. And so we can kind of consider these to be our basic sort of fundamentals for the next month or so. Larmor's formula is not relativistic at all, right? We had a very classical derivation of it. And so this really can only be applied and is only valid in reference frames where the velocities are much less than c with respect to the radiating particle. And so here we can treat these particles moving at a nearly, they can be moving at nearly the speed of light in the observer's frame. But what we do is actually we use Larmor's formula in the rest frame of the particle, where it's not accelerating very fast, or it doesn't have a speed close to the speed of light. And then we'll transform what happens in the rest frame of the particle to the observer frame. And in that way, this thing still ends up being fairly valid, but we can also treat situations where the particles appear from our perspective to be moving at close to the speed of light. And this is you might think this is a little bit of a trick, and in some sense it is, but it seems to work. So the other aspect of Larmor's formula is that it doesn't incorporate any type of quantum mechanics, right? So it's not bound to the quantum mechanical constraints as yet. And so we have to be careful because we're working with electrons, right? So in some sense, there is going to be a quantum mechanical correction that has to be applied. So for instance, Larmor's equation would very incorrectly predict how electron behaves within an atom, right? The electron is moving around in an orbit around the atom. So it is going around, right? So it's accelerating, even though its average velocity might not change much. It's moving around, and so its vector is changing, and therefore it's accelerating, and therefore it should be radiating away. And if it radiates photons away, it should be losing energy, right? Or something should be putting energy into it. And of course, a hydrogen atom in a ground state doesn't have any energy to radiate away or to put back into it. So obviously this can't work in that situation, right? Okay, so another thing that's important to understand about this radiation is that it comes out 100% linearly polarized in the direction of the velocity and this unit vector n. And so we actually have 2 situations. And one situation is where we have this electron accelerating this direction, and also we have the velocity in this direction. And in this case, the radiation goes perpendicular to that. Another situation we might have is, say, we have something which is in an orbit. And so actually its acceleration is in this direction, whereas its velocity is in this direction. And in this case, these are perpendicular to this acceleration. And so we have this basically parallel now to the velocity. And these are kind of two situations we'll encounter a decent amount. And so this was this plot that I showed you when V is very, very much less than C. And so what happens is when V ends up becoming very, very close to C, you end up getting an asymmetry, which is induced in this radiation field. One side is relativistically boosted with respect to the other side. And this is due to the velocity coming back here. So if you have this situation where the velocity ends up being very, very close to the speed of light, this side is strongly boosted compared to this side. And so we end up with a amplitude pattern which looks like this. This is the direction of acceleration. This is the direction of the velocity. One sort of example, just to give you a visual impression of this, is this is an electric dipole field, which is varying by a magnitude of 10%. And so it's just oscillating. And this is the field that it ends up inducing. And so you can see, again, this toroidal shape, which is imparted on this from oscillations in this direction. Okay, so we use this as a way of giving you some intuition. And so we've just been talking, these are the patterns or the field amplitude and ultimately the power that's radiated out from a single electron that's moving or being accelerated. And so in typical situations, we don't just have one electron, but we'll have an ensemble of electrons, right? We'll have an ensemble of charged particles. For instance, we have a hydrogen cloud, and we stick a source in the center of that hydrogen cloud, an O star, for instance, and it ionizes that region. And so all of a sudden we have an ensemble of charged particles, all of which are potentially radiating, right? And so we'll start to examine how we would deal with those situations. And so in principle, you might say, okay, well, it's trivial. Let's add up all of the independent particles, just sum over everything. And well, we have this radiation. And so that's sort of okay, but there are a couple of problems with that. And one of the problems we have is that when we derive the previous equations here, we were using delayed times or retarded times. And these retarded times are potentially different for each particle in this ensemble situation, particularly depending on how far we are away from this ensemble of particles, right? If we're relatively close with respect to the size of this ensemble of particles, we're going to see different delays from this side versus this the back side. And so we also might see delays with respect, if we can resolve it on the sky, we might end up seeing some delays. So we need to, in astrophysical terms, typically we can make approximations, and we can sort of use these approximations to kind of sum this up. And so I'll give you a few examples in a second. The other thing we have to do is account for the phase relations between the different particles. And this can be particularly non-trivial when we're trying to add these all up. And so what we want to do is find regimes where we can simplify this and simply add these contributions from each particle up. Okay, so what sort of situations do we need to have? So we have to deal with some system. It has a length out, and the typical time scale for changes of the system should be tau, some time scale tau. And so we won't notice changes in the system if tau is much greater than the light crossing time of this system, right? And what we really talk about here is that the system ends up being, the changes here have to be coherent. And so they'll happen on timescales which are longer than the light crossing time. Otherwise, if this side of the cloud was changing and this side wasn't, that would be incoherent. And so we want to have something that is coherent. Another way of thinking about this is to convert this time, excuse me, into a frequency. And so this, basically this frequency would be 1 over tau. And so this requirement here is equivalent to a requirement where this frequency, or C divided by this frequency, or this wavelength, is much greater than this side scale. And so that's actually a little bit trickier to do because the wavelengths that we're talking about are pretty small. And so having this be much larger than this could be tricky. But basically we have to have the system is smaller than the emitted wavelength. And if that's true, we can ignore the size. And this then again applies obviously to longer wavelength emission more rapidly than it does to shorter wavelength emission. Right, the size of an atom, for instance, or the size of sort of interaction of a proton with an electron, that may be equivalent to certainly a radio wavelength, no problem, an infrared wavelength, maybe an optical wavelength. When you start to get to gamma rays, the size scale ends up being, of the order of the crossing time of a proton, and so then it becomes a little bit tricky. Finally, here we could characterize this time as the time it takes for a particle to change its motion substantially. And so if we think about a particle path, the orbit of a particle as having a length L and V is its velocity, this time scale for change is equivalent to this orbital path divided by V. And this would imply that V divided by C has to be much less than this little L divided by the size of the system L. And so if we have this definition that L has to be less than big L, what we end up getting back is simply that the velocity has to be less than C, or we basically have a non-relativistic assumption coming back at us. These are just different ways of characterizing the system. So just to make sure that we're in the right regime. Okay, so let's take some ensemble system, right, and has a size of L. And so this system is emitting, it has electrons and protons, it's emitting, and we're the observer out here. And so we can take the total amount of the electric field here from this radiating away as the sum of each individual portion and each individual radius, right? And each individual radius is R1 like this. Now, if this Ri is large compared to differences in Ri, so this distance is much larger than this distance, right? Then we can substitute in this, and all of these things are more or less at the same physical location, and it's just a perturbation of R. And if we do that, then we can convert this sort of thing and say, okay, this amount of this electric field is proportional to the unit vector n cross product with the unit vector n cross product with this thing, which is the dipole moment. And so this, if we have a dipole, which is some charge and some distance Ri, which is here, then if we take the double derivative of that, that is this thing, right? And that is just the double derivative of this, which is an acceleration. So it's a charge times the acceleration. And so what we're doing here is just taking the cross product of the unit vector with the acceleration, and the charge moves out here, and then the cross product of that. And then we're dividing by this constant, which is the total the total distance here. And so this is equivalent to this, right? So here's the charge, here's the acceleration. All we've really done is just kind of compact this down and turn this into a sort of local acceleration. Okay, so we still have to evaluate this at some retarded time, but now the issue here is that we can do this for a point in space which is centralized around the sort of center of the cloud. And this simplifies the equations quite a lot. So we can then think about the power radiated out per solid angle. And this power radiated out per solid angle is going to be proportional to the dipole moment squared, the angle squared, and some constants. And so if we sum over all solid angles here, right, summing over all of this, we end up with just the total power is equal to the dipole moment squared times some constants. And this thing is very equivalent to, right, this is just the acceleration squared and the charge squared. And so if we go back to this, right, it's just these two. And this particular sort of notation is known as the dipole approximation. And so we basically, this just generalizes this formula for a single non-relativistic charge. And so we can think about this system, and it's going to have an instantaneous polarization, which is the electric field. That polarization is going to lie in the plane of this dipole and this unit vector n, which is in our direction, right? And so coming back again to this, so this sort of scenario, when n is aligned with this, then this thing is going to be 0, right? When n is perpendicular, we get a maximum. And so we end up getting that this thing is equal to this. And that's, of course, where we get the sine squared theta. So this should be relatively straightforward. We're just making a slight change in nomenclature. And so what we want to know is we had the total energy radiated away. And what we want to now calculate is the spectrum of that energy. And so we can think about the time derivative of this electric field. How this is varying is directly related to how the acceleration varies and whatever angle we're looking through it at, right? And so these values have amplitudes which may change with time as well. And so we can think about the spectrum that would be radiated out is going to be the amount of energy radiated over some small frequency range. And for the moment, we just use omega, but these are trivially different from frequency nu by just 2 pi. And so we want to determine this energy that's irradiated into some solid angle. And so hopefully you can start to see where we're going here. We have a time change, and of course we can take the Fourier transform of this thing to get a frequency change, right? So we use Parseval's theorem. And so we have basically, this Parseval's theorem asserts that the integral of the square of a Fourier transform of a function is equal to the integral of the square of the function itself. And so we can rewrite the change in energy as a function of solid angle as sine squared theta, and then the integral of this acceleration over time for all time. And we can then use this Parseval's theorem to equate this thing with an integral over all frequencies, with dipole as a function of frequency. And the only change here is we end up having a factor of 2. And this doesn't really make sense because we don't really have all frequencies. And so going between 0 and infinity, we have an extra factor of 2 there. And so we end up getting something which looks like this. And so these two things are equivalent, right? Going over all time, past to present or past to future, is the same as going over all frequencies. And we can also use the fact that this this dipole moment is equivalent to the actual dipole itself. If you take the derivative of it, you will get 1 factor of omega. If you take the double derivative of it, you get 2 factors of omega. And so we have this quality. And so we can substitute for the dipole moment here, the double derivative of it, we can substitute this dipole. And we substitute, because this is squared, we substitute omega squared or omega fourth. This can be pulled out. And we end up integrating over all of this. And we end up with, well, actually, we don't integrate over all this. We remove this, we put this on the other side. And so we have the change in energy as a function of the change of frequency, as a function of the solid angle, is proportional to this quantity here. And this thing again is now this charge and the position, but changing as a function of frequency. And we haven't really defined that yet, but we now at least have a way of tracking the energy as a function of frequency. Is everyone with me so far?
Yes, a question, please.
Yeah.
Are there theoretical and experimental studies about the derivative of the acceleration?
So the triple derivative of t. I think there are. Certainly you can have a change in acceleration.
Mm-hmm.
That can happen, particularly I think there's some systems, particularly ones you induce, where you could manufacture that. Yeah, I don't know. We will actually come to talk about that in a little bit. We will talk about actually something known as a reaction force, which is it uses the triple derivative. It's a fictional force to some extent, but it does have some basis. I don't think I've answered your question at all, but yeah, in theory you can track it, and so you could explore how it actually changes.
Thank you.
Other questions? Okay. Let's see. I'm going to mute you, Roy. You're still your microphone's still on. I don't know. Okay. Right. So we also, if we average or if we integrate over the solid angle, right? We have the solid angle. Oops. Come back. We have the solid angle. If we integrate over this, we should just get a 2/3 that comes out, just the average. And so we can just have a spectral energy density, which is the change in energy as a function of frequency, which is just related to this dipole moment and the frequency of the fourth power. And so this is the spectrum that's radiated directly from a dipole moment. And this thing is just a classical derivation. And so it's valid in classical sense, but as you go to relativistic cases, this thing breaks down. We have to have modifications for that. And based on these arguments, we could make a similar sort of case for generalizing the potentials. And so remember, we had the charge potential and the current potential. And these things are, we have this is a function of frequency, which is related to the change in the charge potential, and the current potential is a function of time. And we can relate these things via this complex exponential, right? So if we integrate over this, we get that. Just doing Fourier transforms between our favorite quantities. And this way we can figure out the potentials as a function of frequency via the functions of time, right? So we can use this kind of all over the place, this trick. So with that in mind, recall we had talked before about this potential being just a charge and some velocity, the charge potential, and then some trying to locate this charge in space. It's basically a delta function, right? And so,
Franz,
yeah,
I have a thought in the previous slide. Yeah,
sure.
here, when we talk about frequency, here we are talking about the frequency in the Fourier space, or we are talking about the same frequency that before in the sharp one?
So we will end up equating them. The only difference ends up being 2 pi in the end. But for the moment, it's frequency in Fourier space.
Oh, okay.
Yeah. But the idea here is that this thing will have an oscillatory behavior, right? And that oscillatory behavior is this thing. And so right now what we're talking about is the field. But at some point very soon, we will convert that to that field is technically light traveling. And that light has some oscillation, which is its wavelength and frequency. And so very easily, we can turn this field oscillation into the actual frequency of light. Does that make sense?
Yeah.
Okay. Okay, so I just want to remind you, we talked about this last lecture, and we talked about trying to derive this current potential and this electric charge density. And this charge density we had to sort of come to terms with the fact that it was moving, and therefore we had to localize it. And so we have this delta function, which is both its original position, but also taking into account that it's moving. And so that delta function has a time component as well. And we can remove the charge from this, and we have this sort of ugly little derivative that we have to do, which is a Green's function. And so we need to sort of solve this to end up getting the charge potential. But that we naturally had a time component here, right? And so we can naturally think of this time variation as leading to a frequency variation. And so we had calculated, again, doing this variable substitution, we had calculated this substitution saying, okay, we're going to have some generic distance r, which is very, very large compared to what's happening on the local level. And then we would calculate the local effects and have this r sort of drop out of that integral. And this gave us these sort of what we call the Leinard-Weichert potentials for charge and for current. And these were this R factor here, which is taking into account this small change, and also this weird thing here, which this kappa, which is in essence it will end up being something which takes on the Lorentz transformation behavior and it sort of takes on a beaming effect. That's where our beaming effects will end up coming in. But this is the difference between this velocity and this unit vector as a function of time. Okay, so this thing, we notice that these have a 1/r behavior as before, as for our sort of the classical derivation of the perpendicular electric field. And we also notice that when v is 0, right, when there's no velocity, this ends up, this is 0, this is 1, this is 1. This ends up being the same, right? This is 1, this is just q/r, and this is 0. So when the charge is stationary, there's no current, right? Makes sense? And we just have a charge. When this isn't 0, this isn't 0. And in fact, that ends up meaning that the magnetic field isn't 0. And there's a magnetic field which is induced or generated from this movement. And these are two consequences of these extremes. Okay, so we can take those two equations, right? So this thing here, well, this thing, and we can take this, and we can end up having some current density, which is a function of the charge density, and divided over this r, with this r minus r prime. And this is this difference here. This is r prime, and then this delta function. And so if we take the Fourier transform of this via this equation here, so whoops, via this thing, so not that thing, where is it? Here, this thing. So if we take that Fourier transform, we, through some, a few lines of code or of math, we end up with something which looks like this. So it has this form, it has this here, and what we've ended up doing is taking this time and this delta function and packing that into this frequency parameter. So now instead of this time variance of the charge density, or sorry, the charge potential, we have a charge potential which is varying as a function of frequency. And this gives us our current potential. And we can make note of the fact here that this K here is simply the frequency divided by C. Okay, so we have now a relation between the Fourier components of these two potentials. And we can do this for all points where if R is very distant from our source, which has a size L, we can make an approximation that this thing, this difference between these vectors and the absolute value of this is approximately equal to our distance to the entire thing minus a unit vector here, dot product with this thing. And so if this thing is perpendicular, then this is 0, right? And we just have R. If this thing isn't, then we have some perturbation on R. And this thing maximally will be proportional to L, or half of L. But more or less it's of the order of L. And so this thing then could become, we can take this and we can make this approximation and we can pull out this portion, which is the effect of the retardation from the source as a whole. And then this portion, which is from each individual element. Right, just assuming that this is a perturbation on the whole thing. And so then all we really have to do is evaluate this thing. And that's a little bit easier to do. Again, is everyone with me so far? Take your silence as a yes. Okay, so again, we're going to take a very non-relativistic approximation. And for this to work, we need that the wave number times L has to be much less than 1. And then if we can do that, if this thing ends up being small, then we can expand it as this to the nth power here. And so, right, so we're just taking this integral and we're expanding it as a summation. So we have a summation over all n for different values of this. And so this is your monopole, dipole, quadrupole moments, if of this term. And so this is an expansion about this value here. So this particular value is going to be complex for n equals 1. You do end up having a dipole moment, which is not complex. And so the dipole moment looks like that. The quadrupole moment, again, is going to be complex. But there are some cases where when you evaluate this, it might end up being something not complex anymore. But the key one, the one that's dominating here, is going to be the dipole. And so here the frequency in this vector potential and the current density are equal. But what's sort of important to note here is that these could actually differ from actual frequency of a particle orbit. So if a particle is orbiting in a circle with an angular frequency omega naught, this charge potential, it contains this, but it also will contain all of the overtones as well. So all of the different moments of that. And so as I mentioned before, typically this dipole moment will dominate. But there are occasions where higher order moments, octopoles, what have you, may also be important and may contribute non-negligibly. But we'll typically be dealing with the dipole. And you should have thought, oh, dipole, that's interesting. We were just talking about a dipole, right? And that is somewhat intentional. Okay, so one immediate application here is to use this to look at what happens with a free charge interacting with an incoming wave of radiation, a photon of light. And so this particular situation, right, we have a free charge is going to radiate in response to its interaction with some radiation. And oops, I changed this, but I didn't change that. I'll quickly do that. I was trying to get the right notation everywhere. My fonts are weird. There we go. That didn't quite, the fonts are still weird. Okay, got it. Okay, so we have some electron here, and it's has a charge in this direction, and so this charge is going to receive this radiation and oscillate, and so this is going to oscillate with a velocity much lower than c. So we're in the non-relativistic regime. We can ignore self-induced magnetic fields and so forth. We're going to note that the E and B fields are identical, equal for linearly polarized electromagnetic radiation, which is what we're going to have here. And this EM wave is going to exert a force on the electron, which is going to be equal to its frequency, its amplitude, and this unit vector. And this force is going to generate a dipole. Right, so we can consider this this force is equal to m times a, and this is going to be our dipole moment. Okay, so that's the situation. And then at some point in time, as this thing is oscillating, it's going to radiate away a photon. Right, it's going to, if this accepted this radiation, it changed and gave it an impulse or an acceleration, a force here. And so now it will change its electric field and radiate that away. So we can think about this in terms of our dipole moment again. And so we have D equals just R times our charge, which is the electron. And so our acceleration is just the charge squared, the amplitude of the electric field divided by the mass, this unit vector, and this oscillating component. And so our dipole, we can solve that, and our dipole equals something which looks like this. And we can define the amplitude of the dipole as just this quantity here, all of our constants and the unit vector. And so now we can define the energy incident upon the electron. And the energy incident upon the electron is just the square, it's the pointing vector, the pointing flux. And so it's just the square of the electric field, or E times B, right? E cross with B. And it's going to be, it's time average, so it's going to be 1/2 of this. That's where this extra half comes in. The 4 pi comes in from the solid angle. And so given this, we can define a amount of power radiated by the electron. And so this amount radiated is going to be this power per solid angle. So over some portion of solid angle, it would look like this. So it has a sine squared theta dependence. And if we integrate it over the entire thing, the power would equal this, right? Okay, so
sorry,
yeah.
I have a question here. This delta of the power radiated comes from the previous part when we obtained the last Moore equation?
Yes.
And in this case, we are assuming that the value of R is 1, or because the integral, the R square value is cancelled with other terms, and at the end we integrating this in the angles theta and phi, and
yeah, well, the R squared term is kind of hidden here in the acceleration.
okay.
Right, so let me get back to here. Yeah, so this thing, we end up having an acceleration, which we actually substitute out at some point. So basically what we have here is we're equating this force, which is this thing here, right? We're moving the m over, and so now the dipole, the acceleration is equal to that.
Okay.
What we're effectively saying is that we have some incoming radiation, it's completely absorbed, and then the electron now is accelerated, and so it oscillates, and that oscillation radiates something away. And in doing that, what we've actually done is created a scattering where we have this incoming thing is scattered, and you have a balance of energies here. But in doing so, this has some angular dependence. And so we actually are able to kind of derive the angular dependence of that.
Okay. Okay, thank you.
Okay. So, right, we had these two equations from before, and all we've done is just substitute out this value here, or you know, subbing in this value, but we've integrated over this. So we have a time average portion of that. So we've just given this as 1/2 rather than 1 or 0, right? Okay, so ultimately what we can divide this up into 2 portions. And one portion is the average flux, which was incident upon the electron, but also is being emitted by the electron. And then some solid angle as a, or sorry, some cross-section as a function of solid angle. So that's simply just taking sort of this portion of it and say, okay, we can divide this into a portion which is equal to this, right? Which is this portion, this thing here, this thing, and there's a C over here. And then we have some portion which is related to the cross-section as a function of the solid angle. And how do we actually get this thing? So we have this, and so we can calculate what this is. And so what is also sort of useful to note is that we have the incident flux and we have the power radiated out. And that ratio gives us the cross-section. And so this cross-section ends up being the cross-section for Thomson scattering. And so we have this thing, whoops, we have this thing, we have this, right, plugged in. And so our cross-section ends up being just equal to these two, and it equals this messy thing or just this, where this is now the classical electron radius, which is just the charge squared divided by mc squared, the mass of the electron. And so this, we calculated out, this is the Thomson cross-section. And we, just to sort of note, we came about this in a very unusual way, right? We were taking Larmor's formula, and generally we were saying, okay, we have some radiation which is absorbed, and the electron gets an impulse and then radiates that away. And so our schematics for this was a little bit obscured in that we were saying this was absorbed and then radiated. But ultimately, we could think of the whole process as happening so fast that it's not absorbed, but that you get some conservation of energy, and this ends up being a scattering process. So this whole process, it's non-relativistic. It's very far outside of the quantum limit. And in these two limits, this is what's known as Thomson scattering. What's important here is that there's no frequency dependence here at all. And so the scattering will affect all energies or all frequencies of light the same. There is, if you go back here and you say, what is the cross-section as a function of the solid angle, there you do have a sine squared dependence, right? Because this has a sine squared dependence. And when we integrate over all the cross sections, then, or sorry, all of the solid angles, we average over this, or we get rid of this. But for any individual one, we have a dependence. And so this cross section has a dependence on the angle that comes out. So there's a preferred angle, potentially. Okay, one thing to note here, this thing obviously breaks down when you have very high frequency light. So that the energy of the light becomes comparable to the rest mass of the electron. And so obviously there we have to then talk about Compton scattering. And then another thing we might have to do is take into account quantum mechanical cross sections, which will differ from this. There's a correction factor in that. Questions? Okay, so we can think about the polarization of this. And so initially we had something which came in linearly polarized, one sort of photon of light. And so strictly speaking here, these calculations are made for polarized radiation, which is incident upon an electron. And we chose the E fields to be coming in the same direction. And this is a very idealized case. This is not likely to be true for most purposes, right? And so the benefit here is, of course, that this doesn't really end up making much of a difference. And we end up recovering the value of Thompson scattering regardless of whether the E fields are coming in, in this direction versus this direction. That's fine. And so this, basically the electron is free to oscillate in any direction. And so this kind of takes care of this directionality of the E field. Now this, one of the things to note here is that because this can take sort of any directionality to it, and the electron can oscillate in any direction, what this means is that if you have a light that's coming in polarized, then this process will randomize that polarization. And so if you have light that, a bunch of different light that's coming in, it will come out randomly. So it will come in polarized and come out unpolarized. Now, that's not exactly the case, because what we end up having is, if we have a bunch of electrons which are oscillating in different ways, we will have some cross-section which preferentially prefers a certain direction. But because there's an ensemble of electrons which are all doing different things, that's what ends up randomizing it. And hopefully this sort of makes it clear. So if we have something which is coming in and they have a polarization direction, which is coming like this, and the electron is oscillating in this direction, the preferred plane of scattering is in this direction. So it's perpendicular to the incoming polarization here and the oscillation. If we have something which is coming in here and this is oscillating in this direction, we polarize it like this. If we have something which is coming in all directions, essentially it's unpolarized, and you have oscillations in many different directions, what ends up happening is that you polarize some radiation, or you'll send some radiation in this direction, you'll send some in this direction. This will end up being polarized, this will end up being polarized. But what you end up sort of getting in this direction will also remain unpolarized. And in this direction will remain sort of slightly polarized or slightly unpolarized. So basically the degree of observed polarization depends on the viewing of the observer with respect to this situation. So you can have unpolarized light come in and it can end up coming out polarized. So it's a bit sort of confusing. But this is sort of how this situation works. Okay. And so one of the key things here is one of the interesting situations is, let's say we have radially emanating light that's coming out and it's relatively unpolarized. And you have a screen which is electrons. And you happen to block our line of sight to the initial emitter. And so all we end up seeing is the radiation that's scattered. And so in that case, we end up seeing radiation which is highly polarized, because we're in a very preferential geometry with respect to the emission and the scattering medium. And this is, of course, this is actually a physical situation we see, for instance, in obscured AGN, where we have a torus or a galaxy which is obscuring the central source, but we have some ionized gas above it or below it, which is preferentially scattering. So it looks like this, but we're an observer here or here. And so we end up seeing radiation which is strongly polarized because of the medium, not because the original radiation was necessarily polarized. This also happens for star formation regions where we might see a cloud blocking the line of sight like that, but then off to the side there's a view that's open and it's ionizing radiation. It's ionizing a path in that direction, and so we end up seeing the scattered light. Okay. So we can also estimate the differential cross-section here. And we have to recognize that we have a, sort of an unpolarized beam can be regarded as an independent superposition of two linearly polarized beams with perpendicular axes. And so we can choose one beam to have a unit vector E1, which lies in the plane of the incident photon, and then another one, E2, which is perpendicular to this. And so we can derive a differential cross-section for unpolarized radiation as basically the average of these two cross-sections of linearly polarized radiation coming from these two different sets. And so our unpolarized cross-section as a function of solid angle is just the combination of this thing, so this angle here. So this is the situation. We have a unit vector E1, a unit vector E2, and are actually coming out in this direction. So we divide this into this component. This unit vector with respect to E1 is given by this theta, and then this unit vector with respect to E2 is given by pi divided by 2. And we also have a unit vector k here, which is the actual unit vector of light. This is the wave number. So with respect to this, we also can define theta as equal to pi squared, or pi divided by 2 minus this capital theta. And so we have these two portions which are related to these two different unit vectors. And so this thing, if we sort of divide it out, this will end up being related to sine squared theta and 1 times our r squared here, where I have to come back and find this. Right, so we have this thing, and we can actually substitute back in our classical electron radius for E squared divided by MC. And so we end up having this cross section is related to our radius squared times this component here, or times this component here. And this will give us the cross section for unpolarized light. And we could also calculate this for polarized light, and it would be slightly different. But it depends on where it's coming out, right? So depending on how this changes, your cross section changes. How much radiation is coming out. And in particular, this will, for certain polarizations, so if we have something where theta is equal to 0, then this ends up being 0, and we have the full cross section. And if theta is equal to 90, then we actually have something larger than that, right? We have 2 divided by that, so we end up having just r squared, and vice versa here. Okay. So there's a few interesting results here. So this in particular demonstrates that there's a forward-backward symmetry, right? Because we have the square of these angles. And so the negative versus the positive gets lost in the square, right? And so this is scattering, which is symmetrical under reflection. The total cross-section that we get out for unpolarized light should be about the same. Basically, it should be exactly the same as we get out for polarized light. And so when we add these two up, and when we take everything together, we should end up getting the total amount out in the end if we integrate over everything. So this thing should equal this thing, which should equal 8 pi divided by 3 times this in the end. And the rest electron will have no net intrinsic direction. The polarization of scattered radiation is going to have 2 terms, and these are going to refer to the intensities, which are perpendicular to the directions in the plane normal to n. So the outgoing radiation will have some degree of polarization. And that degree of polarization is related to, or it can be given by these two polarized intensities, the plane and perpendicular polarized intensities. And they're going to have a ratio which is related to cosine squared theta divided by 1. And so we can define a degree of polarization, which is quantified by this. And so if we have unpolarized light, that unpolarized light can be completely polarized depending on the direction of the observer. And so if theta ends up being equal to 0, right? So this is equal to 1, this is equal to 0, and there is no polarization. The theta equals 0 means this angle is 0, and so the scattering just sends it in the same direction it was going before, or vice versa. If it scatters it directly back, there's no polarization. However, if theta is 90, this drops out, right? This is 0, this drops out, and you have full polarization. And so scattering in this direction gives you full polarization. So the observer sees 100% polarized light, as I was mentioning before. Okay.
Sorry, I have here a question because despite the explanation of the different components of the polarization, I didn't understand well exactly mathematically that degree of polarization is obtained. Because I remember that degree of polarization is, can be calculated as the ratio between the intensity, the polarized intensity over the total intensity. But I don't know here how this degree of polarization is found.
Well, so basically what we're saying is we have we end up having light which comes in and it's scattered out in some direction. And depending on this direction, you will have a strong degree of polarization or not. So there are only certain polarizations which will be scattered in this direction. So if you have a bunch of light coming in, which is unpolarized, what will happen is this thing acts as like a filter or cone, and only certain polarizations incident that are coming in will be scattered in that direction. Because this depends on the oscillation vector of the electron. Right, so coming back to this. And so this oscillation vector dictates in what plane the radiation will be scattered out. And so there will be no radiation scattered in this direction for this particular geometry. Right, and so what this is doing is picking out certain polarizations and preferentially scattering them in this direction. And what it ends up doing is it picking out certain directions and scattering them in this direction. And so when you have something which is no longer polarized coming in, what will end up happening when you have this interaction is that you will preferentially scatter certain components of this, i.e. these vectors in this direction, and these vectors in this direction. And so you will end up having 100% polarized light coming out here, although some of that light will be scattered in other directions because it was polarized differently. Right, so the total will never, if you take this amount of intensity divided by this intensity, it won't be 1. And it will be actually much less than 1 because there's a probability of scattering, right? This particular polarization has a probability to be scattered in this entire plane. And we're just sitting here in one portion of that plane intercepting a solid angle. So we're never going to see all of it anyway. But we can see a polarized portion. is the point. And there are certain angles where you might see both, right? So this will scatter, for instance, here, we actually will end up scattering both equally. And so we'll end up seeing something which is, it came in unpolarized, it comes out unpolarized. But there's an intermediate angle where we might see a component of both. And so that's what this is trying to show, is this difference between the plane and the perpendicular components. Does it make more sense now, Laura?
Yes, yes.
Go through it and try and work it out in your head once,
Yes,
and see if you can.
I will try to work on the specific mathematical form of that degree of polarization. But yes.
Yeah. I mean, the trick here is that this electron can oscillate in any direction and will be picked up by the normal of this component. If this doesn't really have any preferred direction, then it will sort of be randomized. But the cross-section as a function of solid angle will not be randomized. So it will proportionally scatter some radiation only in some directions. That's all. Okay. Yeah, dealing with polarization is not trivial, unfortunately. Okay. So a few other sort of things to think about here. So for low energy photons, h nu is much less than the rest energy, and this works fine, right? So we have V much less than C, and we reduce to the classical Thomson scattering. We consider this scattering coherent or elastic, because the incident and scattered photon energies are equal, and the electron doesn't recoil. Now, these assumptions break down in two important ways. So one, when we have high energies, we get an electron recoil. And so we have to actually factor that in, which is known as Compton scattering. The other is when you start to have, say, relativistic effects which creep in, you end up modifying the cross-section, and you have to account for quantum mechanical effects. And this changes the actual cross-section. Okay, so now, let's see, I think we're actually sort of out of time. And I was just about to come to Roy's question, which was radiation reaction force. So let me introduce radiation reaction force, so it doesn't come as a complete surprise to you on Wednesday. And then we'll pick this up on Wednesday. So basically, we can think about this process or hypothesize that there is a force acting on a particle by virtue of the radiation that it produces. And so this particle is say, oscillating, and it's radiating away. And we can have a force which is equal and opposite to that. And this would be known as the radiation reaction force. And we can kind of use this to gain some insight about this without really having a rigorous mathematical treatment yet. And so what we want to do is induce a perturbation on a particle motion. And so we have basically this radiation reaction will produce this perturbation. And so we want to have some time interval t over which kinetic energy of the particle is changed by some substantial amount due to some radiation which is absorbed or emitted. And so this time scale will be related to the total kinetic energy of the particle divided by the radiation emitted, right? The energy per time. And so this is energy per time, divide them out, and you get a time. And so we can plug in our Larmor formula here, and we get out something which looks like that. And so these are all constants. And so this time here is more or less related to this time. And we can estimate velocity divided by acceleration as a typical orbital or oscillation timescale. And presumably the loss of kinetic energy should greatly, or this kinetic energy loss should exceed this orbital timescale, meaning that on one orbit, it's not going to lose too much of its time or of its energy. And another way of stating that would be that this time scale has to be much larger than this time scale, such that this ratio is much larger than 1. Or this time scale has to be much larger than this time scale, which is the light crossing time across an electron radius. And this thing is, this light crossing time for an electron radius is just this classical value, which is of order of 10 to the minus 20 seconds. So this has to be larger than this has to be larger than this. And this implies we would treat this as a perturbation. And so we'll have a time average radiation force, which is going to be defined by the spatial derivative of this energy radiated times time. Right, so this is the total amount of energy, this is the spatial derivative, so it should be a force. And so this reaction force is related to the double derivative of our velocity, or the derivative of our acceleration. And so we can think of this as, right, this is just this thing here. So we have P and we have this T. And so we can think of it as something which looks like this, or it looks like M times this time component times this change in acceleration. And obviously this triple derivative means we need a super elaborate equation of motion. And so we'll think about this in more detail when we come back on Wednesday. But Roy, I wanted to introduce this so you saw that people have thought about it. Okay, so I'll stop here and we'll pick back up with reaction force on Wednesday. Questions?
Sorry, I have another question.
Okay.
Well, it's related to the new topic. I was wondering why the time for light to cross and radius of the electron is r0 over the speed of light. I don't understand why these 2/3 terms appears here.
Okay, well this we defined earlier, right, which is right here. That's just this. So this divided by c is just going to be e squared divided by m divided by c to the, well, actually it should be, yeah, no, it should be r divided by c. And so it should be e squared divided by m divided by c cubed. So what do we have here? Yeah.
And these 2 and these 3 doesn't change too much, or disappear?
Yeah. So that. So where the hell does that come from? Yeah, I forget exactly where those come from. I need to go back and look at what those are. But no, it doesn't. I mean, these are all like squiggles, so they're approximately anyway. But yeah.
Okay. Thank you.
Yeah.
Yes. Is there a classical or quantum analogy of this radiation reaction force?
Well, the classical version of it is this. The quantum mechanical version of it, yes and no. Yeah, I think you end up having to do a complete reformulation of this, so you don't have an exact replica of this.
Okay.
Yeah. But I mean, we do have some, so deriving this in this way, it's not, I would say, very intuitive, at least not for me. But in doing so, you can come away with some formulations of different fundamental processes which seem to behave in that way. So I wouldn't say that this is super intuitive, but the end result ends up being something which is observed in nature. And so there is some basis to it, clearly. But I think the way we get there is not necessarily the most straightforward. I mean, does that make sense, Roy? And you could probably try and sort of rationalize, you could try and rationalize this a little bit better, maybe, I think. Or try and find ways of saying, okay, this is why we do this. But really what this is something else. And so maybe having some intuition about that, how to flip that would be good. I personally don't have it, so I can't impart it to you. Yeah. We will move away from it. It's just mostly to give some intuition about how things relate. And this largely comes from Rubicki and Lightman, and then they took it from other people as well.
Mm-hmm.
Right, but it mostly comes from a Newtonian sense of classic mechanics, and so trying to say, okay, we have something which is radiating away, and so it's losing energy, and so we can try and equate it to something which is inducing that, right? Or having an equal and opposite reaction.
Mm-hmm. Okay.
Yeah, but in some sense, I mean, all of the emission of radiation has to end up having a sort of quantum mechanical basis, right? You would expect. And so all of the derivations which are done classically clearly can't get at that. Yet most of the derivations are done classically because we don't necessarily have an understanding of how quantum mechanics can do that. Or the math is much more complex to do that. Okay, anything else?
Thank you.
No? Okay, well, I'll see you guys on Wednesday.
Okay, thank you.
Goodbye.
Bye.
Thank you.
Bye.